Welcome to week 1. I am Professor Danae Madrid, and this is Chemistry 110. So our overall lecture outline, we're going to start with chapters 1.1 through 1.2. That'll be the first set of slides, and then we'll move on to chapters 2.3 through 2.5. All right, let's start with chapter 1.1. What is chemistry? Chemistry is the study of matter. Looking at the first bullet point right here. Matter is anything that contains mass and takes up space. So those are the two criteria. That is really everything around you, from the glass of water to the rug in front of you, to even things that you can't see, like little dust particles or the gas that you're breathing. That still contains mass and takes up space. So everything that you can see and what you can't see is matter around you. Okay, what else is chemistry? Chemistry is, like I'm looking at my second main bullet point here, the central science of the STEM disciplines. So STEM stands for science, technology, engineering, and mathematics. So it really is the bridge that holds all of these disciplines together. Physics is our fundamental science, but chemistry is the bridge between physics and, let's say, biology. Off of chemistry, we also have disciplines like earth science or medicine or different types of engineering. So chemists pride themselves in really being that bridge that connects all of these different disciplines together. Okay, chemistry also utilizes the scientific method. Scientific method is an approach used by scientists to test hypotheses based on observations and experimentation through collecting empirical data, and through that either revising hypotheses or continuing to do further experimentation to form laws or theories. Okay, so an example of an observation is probably pretty obvious. It's something that we observe in the physical realm. We see a pencil dropping off a desk. We see steam coming off of a hot pot when you're boiling water. Those are observations. Hypothesis is like a prediction, saying, okay, I predict that since I see a pencil falling from the desk, if I put a ball on the desk and move it to the edge, it will also fall and hit the ground. Okay, that would be a hypothesis. Experimentation is something that tests the hypothesis through collecting empirical data, testable, observable data. So if your hypothesis was, I predict that all objects, if pushed off of a desk, will fall to the ground at the same rate. What you would do is take a collection of objects, put them on the desk, push them off, and see if they were to hit the ground at the same rate. A law is formed if all experimentation tested multiple times in multiple different scenarios with many different people in many different times in many different ways all holds up the hypothesis that was previously or primarily stated. So a law is only formed if all experiments are not able, let's say, to discount the hypothesis that was previously stated. So an example of a law would be the law of mass conservation. So what this law states is that matter, or anything that has mass, is not created or destroyed in a chemical process. And no experiment has ever disproved this law. A theory, on the other hand, is one that explains a law or observations. So, an example of a theory that would explain the law of mass conservation is the theory that matter is composed of atoms. This is not a law because it is explaining a law. The reason why matter cannot be created or destroyed is because it's composed of atoms, which can't be created or destroyed. Okay, moving on to our last main bullet point. Chemistry is described in 3 domains: the macroscopic, microscopic, and symbolic. I'll give you an example for each. So macroscopic would be something that can be seen. It's on a larger scale. It's observed with the naked eye. So an example again would be a glass of water. Microscopic domain would be something like a bacterial cell. Symbolic domain is something that represents these other domains, something like a chemical symbol, Ag, which stands for silver. Okay, let's move on to our next slide. All right, moving on to 1.2. What is matter? Well, matter is described in 3 basic states. Those 3 basic states are solid, liquid, and gas. So I'm going to explain these in terms of energy. Energy, there are 2 main types of energy. So energy can be what's called potential energy, or PE. Or it can be kinetic energy, which is abbreviated KE. Energy in general is the ability to do work, or energy can be given off in the form of heat. So ability to do work or the amount of heat something possesses. Potential energy is energy by virtue of position. So you can kind of think of a ball on the top of a hill has the potential energy to fall to the bottom of the hill. Kinetic energy is by virtue of movement. So a ball being thrown in the air has a higher kinetic energy than, let's say, a ball on the ground that is relatively still. So this has low kinetic energy. Ball on top of the hill, high potential energy, low kinetic energy. Ball on the bottom of the hill, low potential energy, and at this point, when it hits the bottom, also low kinetic energy. Okay, so if I'm going to describe these 3 basic states of matter in terms of the potential and kinetic energy, I'm going to get rid of this drawing first. So here's my solid, here's my liquid, and here's my gas. Solid particles, you can kind of think of it as, let's say, a little cube of ice. Solid particles have relatively low kinetic energy and higher potential energy. They have bonds that are able to be broken or able to be disturbed, so they have the potential of giving off energy, but they aren't moving relatively fast, so that's why they have low kinetic energy. A liquid, we can kind of think of it as a glass of water, has higher kinetic energy and not particularly high potential energy. It has a little bit lower potential energy as it is relative to a solid. And for gas particles, you can kind of think of them as these individual little molecules of water in the gas phase. Those have very high, so the highest kinetic energy, and they have the lowest potential energy. So liquid is somewhere in the middle. With solid being the lowest kinetic energy and the highest potential energy. I was going to abbreviate that, solid, liquid, and gas. In terms of kinetic energy, we would have low, we would have somewhere in the middle, and we would have high. In terms of potential energy, solid, liquid, and gas, solid would have the highest, liquid would have middle, and the gas would have the lowest potential energy. Okay, moving on to what mass actually is. Okay, mass is not weight, so you don't want to think of those as synonymous terms. Generally, the unit that we use for mass is grams, and that's abbreviated by AG. Weight, we use different different units, but what you're used to is probably pounds that you would use when you weigh yourself on a scale, for instance. Now, what weight takes into account is gravity. So that's why your weight would be different on the moon as opposed to on Earth, because the gravity is different. The force that's pulling you, two bodies with mass together, is different depending on where you are. So mass does not change based on where you are. Mass remains unchanged relative to location. So it doesn't matter where you are. If you have a certain mass here on Earth, you'll have the same mass on the moon. All right, let's continue on to our next bullet point. Matter abides by the law of mass conservation. A law of chemistry that relates to mass conservation states that matter is not created or destroyed in a chemical process. So I'm going to write out for you just a very generic chemical reaction. So when a chemical turns into something else, it's called a chemical reaction. The starting material is called the reactant. And when it is chemically changed into fundamentally a different product, we draw an arrow, and on the right side, we write the product. Now, this is generic because I'm not giving you a particular compound or chemical that's undergoing this process. But if you were to take the mass of this reactant at the beginning, the products would equal the mass at the very end. So there's not going to be any mass that's lost in this process, no matter what the reactant and the products are. All right, so skipping down to our fourth bullet point. The matter map is what we use as a tool to classify matter, and we'll see that in the next slide as well, but it just breaks down matter into understandable categories that we're going to use for this semester. So we'll see that on the next slide. Let's finish off this slide with atoms versus molecules. It's two terms that you'll hear a lot when we're discussing chemistry and we're discussing matter. So all matter is composed of atoms, okay? And we'll go into the atomic structure and what that is a little bit later in more detail. But basically, the current model of the atom describes that the atom contains a nucleus, and it's the very dense center in the middle of an atom, and that is where protons, subatomic particles called protons, and subatomic particles called neutrons reside. And the electrons are on the outside. This is the same as an electron. The electrons are on the outside of the nucleus, and they possess a negative charge and orbit around the center of the nucleus. There's a better word to describe how they actually behave around the center of the nucleus, but for now we'll just simplify it and say that they orbit around the nucleus. Okay, so all matter, like I said, is composed of atoms, and atoms are individual units that contain some number of proton or protons, and usually one or more neutrons and a set of electrons. Now, molecule, on the other hand, has two or more atoms joined by chemical bonds. So an atom by itself is an element that possesses certain characteristics and certain properties. Elements are either composed of one or two atoms that are the same type of atom that are chemically bonded together, and they have a set of properties that they adhere to. So we'll discuss that more in the coming slides. All right, here is the matter map that we discussed on the previous slide. So at the very top, we have all of our matter, and that's broken down into two major categories, either mixture or pure substance. A mixture is something that does not have constant properties in composition, and a pure substance does have constant properties in composition. A mixture is then divided into two different types of mixtures, and that is a heterogeneous or homogeneous mixture. If the mixture is uniform throughout, but does not have, again, constant properties or composition. It is a homogeneous mixture. If it is not uniform throughout, then it is a heterogeneous mixture. And I'll explain a little bit more of that in a second. I'll give you an example of each. Matter that's a pure substance is divided into two additional categories, and that is an element or a compound. So if it can be simplified chemically, so basically can the bonds be broken down into even simpler parts? If it can, then that's a compound. If not, it's an element. So this will make more sense when I give you an example. Let's start with an element. So an example of an element that we get from the periodic table might be, so this Na stands for sodium. That's a chemical symbol for sodium. Sodium, oxygen, which is diatomic. That means in its elemental form is always going to exist with two oxygen atoms chemically bonded together, or let's say lead. Okay, all of these individually are elements because they're all one type of atom. A compound would be something like H2O. So this is water. There's two or more types of atoms and they're chemically bonded together in the same ratio. So that means water is always going to have two hydrogens for every one oxygen. Notice the subscripts are what determine or what tell you the number of each atom that is in that compound. Another example is carbon dioxide, which is CO2. Another example is table salt, which is NaCl. So notice each one of these has two or more types of atoms, whereas an element is all one type of atom. Okay, moving on to a homogeneous mixture or heterogeneous mixture. We'll start with homogeneous. So a simple example of this would be salt water, where the salt is all dissolved in the water, salt water. So when we ask the question, is it uniform throughout? If you look at salt water, salt actually dissolved in the water, there is no, the first rule of thumb is, can you see through it? So that means, is it uniform throughout the entire mixture? That would mean it's a solution because everything's dissolved. You can see straight through. There are no different parts distinguishable one from another. Now, an example of a heterogeneous mixture, let's say a salad. Okay, that's a mixture because you have different parts, just like you do in salt water. In salt water, you have water and sodium chloride, which is the salt. So you have two different chemicals, if you will, that are together, that are mixed together. But the difference in a heterogeneous mixture, let's say the salad contains the lettuce and cucumber and some type of dressing. Okay, it doesn't matter. It just needs to be two or more types of parts. So these are multiple different compounds, and some potentially some elements in there too, all mixed together, and they are distinguishable parts. That means that when I look at this mixture, I cannot see through it. It is not uniform throughout the mixture. There is individual parts that can be easily separated. So a homogeneous mixture, you can separate the salt from the water, but they are not, you have to go through some type of additional physical process to do so. You would have to heat off the water, let it boil and turn into steam so you could have the salt remaining at the end. But in the instance of a salad, all I would need to do is just take out pieces of that mixture and separate them into their component parts. So that's what separates a heterogeneous mixture from a homogeneous mixture. All right, so let's do our first problem. So we have three substances at the top, labeled A, B, and C. A is honey, B, this is salt water, and C is a piece of wood. So the problem is to classify each of the substances as pure substance or mixture based on the matter map on the previous slide. If it's pure, then I have to determine if it's an element or a compound. If it's a mixture, I have to determine if it's homogeneous or heterogeneous. So using that map, you can refer back to it. I'm going to start with part A. So does honey have constant properties or features? No, it does not. It's composed of many different types of sugar, some water in there. So it's not just one type of chemical, and it's not just one type of element. It's a mixture of different things. So that's why we would designate it or categorize it as, I don't want to categorize it that far yet. I want to categorize it as a mixture. Let's do the same with B. So B, what I have here, I told you it was salt water. So we had already used that in an example from the previous slide. So I look at this. This is from the ocean. I know that it's composed of at least two different parts, right? So it's not just one type of substance. So it would not be pure. It would also be a mixture. And then for part C, C, obviously when I look at wood, it is not just one substance either. There are many different parts to wood. So this is also a mixture. So if there are two or more different components to these substances, then they would be mixtures. Okay, let's further classify honey. So is it homogeneous or heterogeneous? So a really easy rule of thumb to use is, can you see through the mixture? Can you see all the way through to the other side? So if I look at honey, it might be distorted when I'm actually looking through a bottle of honey, but you can see to the other side. There are not specific or individual components that are blocking your view. It's all constant. The mixture is constant throughout, and so this would be a homogeneous mixture. Same idea for part B for salt water. Even though there are two different components that are mixed together, you can see through the mixture. It is consistent throughout, and so I would also classify this as a homogeneous mixture. This is different from the wood. Wood I cannot see through. I can actually see certain components. If in this case, you can see there are some darker areas, there are lighter areas. It is not consistent throughout, so this would be a heterogeneous. And not only that it's dark, because as you see in part B, it looks like there's some different colors. That's just from the sun. But actually that you cannot see through part C, okay? It's not a substance that's mixed together in such a way that you can see through to the other side. And so that's a pretty helpful rule of thumb that you can use. All right, so matter classification continued. These are some other terms that you'll want to be familiar with. Let's start with the simplest term, and that's an atom. An atom is the fundamental unit of all matter. It contains a particular number of protons, usually a certain number of neutrons, and a certain number of electrons, depending on what type of element you are looking at, what element that atom is. So the atom, again, is the fundamental unit of all matter. All atoms are types of elements, which is why they're in the same circle. An element is a substance that cannot be chemically interconverted or broken down into a simpler substance. So, cannot be, we'll say chemically simplified. It is always going to contain a certain number of protons. So the number of protons, I'm going to put number of P plus, that means number of protons, gives identity of the element. So that dictates what the particular properties are going to be. A molecule, on the other hand, can be an element and can be a compound. So a molecule, like we put a few slides ago, is just two or more, two or more atoms. They can be the same type of atom or different, chemically bonded. Let me change the color for you. Chemically bonded. We'll talk about bonding a little bit more later. That means they're held together by a force, a chemical force. A compound can be a molecule, but specifically it's two or more different atoms chemically bonded in a set ratio. So for example, something like H2O is always going to be 2 hydrogens to 1 oxygen. All right, let's move on. Right, problem number 2, case components. Identify each as either element or compound. So let's look at the case components. Polymers such as ABS, which stands for acrylonitrile butadiene styrene. Okay, you didn't need to know that. But it's composed of monomers or monomeric subunits, which are just molecules all linked together, the same molecule all linked together. That's what you need to think of. So polymers such as ABS, and then metals such as aluminum, iron, and magnesium. So we have 4 different parts that we're identifying here as either element or compound. So here, here, and here. So ABS, since it stands for, I'll say it again, acrylonitrile butadiene styrene, it is a compound that continues to link to itself to create a polymer. Okay, that's poly means many. So ABS we can classify as a polymer consisting of compounds of a particular compound. Okay. All right, moving on. Aluminum, iron, and magnesium. If you looked all of these up, they all are identified on the periodic table. The full name for that is the periodic table of elements. Okay, so if you see anything that matches on the periodic table, which we haven't really expanded upon so much yet, but you should be vaguely familiar of the periodic table. Each one of these is an element. So that would be the answer for our first part of this question. Second part of the question says to look at the screen components, which is right here, and identify as pure substance or mixture. So let's identify each of the parts. We have silicon oxide, which can also be known as silicon dioxide. And then we have aluminum, sodium, or potassium. So we want to know if it's pure or a mixture. So looking at silicon dioxide, that's actually the name of a compound. If you look back at your matter map, a compound is a pure substance. So the answer here, I'm just going to abbreviate to PS as pure substance. Aluminum, sodium, and potassium can all be identified on the periodic table of elements. Each of them is an element. Elements are pure substances. So I'm going to abbreviate that as PS. So everything that is a screen component is also a pure substance. All right, let's identify these terms so that we know what we're talking about when we're looking at an atom. I said that an atom is composed of 3 separate parts, proton and neutron, and an electron. Protons and neutrons, these two right here, reside in the nucleus. The electron is outside of the nucleus. Okay, so what is a proton? A proton is a positively charged particle that resides inside of the nucleus. I'm going to abbreviate that a little bit. In nucleus, which is in the center, and I'm going to put it has a high mass. A neutron is just like it says in its name, a neutral charge in nucleus and also has a high mass. An electron, which is outside, has a negatively charged, is a negatively charged particle outside nucleus and has a very low mass. All right, so now you have some understanding of proton, neutron, and electron. I'm going to draw up an example. So proton and neutron, they're contained in the nucleus, and an electron orbits around the nucleus. All right, let's move on to atomic symbol. An atomic symbol is a symbol for an element. So these are found on the periodic table, and they stand for an element. So for example, I've used this before. Na is the atomic symbol for sodium. They usually have a Latin root to them, so that's why Na doesn't really make sense in English for sodium. Okay, moving on to atomic number. Atomic number is abbreviated given the symbol Z. Atomic number is equal to the number of protons an atom has. So atomic number is the number of protons, and this gives the element. We'll have practice of this on the next slide. Mass number, the mass number is the number of protons an atom has plus the number of neutrons. So that's equal to the mass number, which is given the symbol A. All right, the charge, let me just erase some of this so it's out of our way. So the charge on an atom is equal to the number of protons minus the number of electrons. So that will give you the charge. I'll give you another example on the next page. In isotopes, isotopes are atoms with the same number of protons, but different number of, nope, not electrons. Just kidding, seeing if you're paying attention. Okay, but different number of neutrons. Simple as that. Okay, so let's look at some examples on the next page. All right, in order to solve problem number 3, you will need a periodic table like the one seen at the top of the screen. So let's look at the first question. Identify Z, A, and the number of protons, neutrons, and electrons in the following. And then we see the notation C-13, magnesium with a 2+ charge and mass number of 25 AMU. So there are two different substances or two different isotopes that are identified here. The first one is C13, and I'll explain what that means, what that notation means, and the next one is magnesium, and it has a couple of identifying factors listed. So what you'll need, like I said, is a periodic table, so I'm going to kind of blow this up so you can see, and we're going to focus on a C13. So I'm just going to identify what that is, where that is found first. So the C corresponds to the atomic symbol. The atomic symbol C is right here, and it stands for carbon. I'm going to erase that really quick so you can see that. I'm going to blow this up so you can see the name. So it does say carbon underneath the C. So that's the first piece of information that we would need. And it says identify the Z. So remember that Z, I'll just scroll this down a little bit. So remember that the Z stands for the atomic number, which is the same thing as the number of protons. That can be found right here. So that's that whole number here. So the first answer for Z, for C13, so for Z13, C13, Z is 6. That's the number of protons. That's what Z stands for. Okay, A is the mass number. Well, the mass number is not found specifically on the periodic table. It is the one listed right here. So 13 is the mass number. It's the number of protons and neutrons together. So I'll put A is equal to 13. Okay, so we did Z, we did A, and then the next is to identify the number of protons. Well, that's the same as the Z, so we're going to say the number of protons is 6. The number of neutrons, that comes from this piece of information, which is A, and Z. So if I subtract the two from each other, that means the number of neutrons is 7, because 13 minus 6 is 7. Next is the number of electrons. So notice where it says C13, there's no charge around it. You don't see any other information. There would be a charge showing if the number of protons and electrons was different. So remember, to calculate the charge on a particular isotope or on a species, you would need the number of protons and subtract from it the number of electrons. Well, in this case, since there's no charge, that means that they are equal. So the number of electrons then is equal to 6 as well. So that's the answer for C13. I want to give you a bit more information, so I'm going to minimize this really quick. There are two different ways to write, two main ways to write an isotopic notation. So the first way is written here, C13. This gives you information about what the atomic symbol is, and then it also gives you the mass number. Another way to write this exact same isotope, but in a different notation, is to write C, and then at the bottom, left-hand corner, you write 6. This is the Z, or the atomic number. And at the top is to write the mass number, which is 13. These are two sides of the same coin. So they give you the same piece of information, but two different notations. Okay, so let's move on to the second part of this problem. So we also want to identify everything above, but for magnesium with a 2+ charge and a mass number of 25. So let me show you what this would look like if I wrote it in the notation that the carbon is written in. So I'm going to erase this. So it says magnesium. Okay, so I'm going to blow this up for you to see and erase this, just so it's not in the way. Okay, so magnesium is right here on the periodic table. Notice this 12 right here gives you what the atomic number is. So I'm going to write it in a certain notation. So we have a bit of information in front of us. So magnesium has an atomic number of 12. That would go down here. And then it says a mass number of 25. Okay, so 25 would go up here. And really it shouldn't say AMU. This stands for atomic mass unit, but just ignore that for right now. The AMU usually is associated with an exact mass, and 25 is not the exact mass. Okay, so that means it has a mass number of 25, and it says it has a 2+ charge. You would see the charge in the upper right-hand corner like this. So those are the 3 pieces of information that you would need to solve the rest of the problem. So really right now I don't need the periodic table anymore. All I really need to look at is this notation right here. Okay, so let's use that to answer the following. All right, so what is the Z? Well, Z, like I said, is identifying the lower left-hand corner, so that is equal to 12. We got that. A is the mass number. That's in the upper left-hand corner, so that's 25. The number of protons, it's the same as our Z, so that is going to be 12. Neutrons is our mass number, which is 25, minus our Z, which is 12. So that is equal to 13. So the number of neutrons is 13. Number of electrons. So remember, on the previous slide, I said to calculate the charge. That equals the number of protons minus the number of electrons. In this case, we have a charge of 2+. So 2+ is equal to, and let me reorient this just so it doesn't confuse you. So I'm going to write it, let's see, I'm going to erase this so we have some room. So charge is equal to number of protons minus number of electrons. The charge is a 2+, stated right here. The number of protons I wrote down is 12, and I don't know the number of electrons, so you can basically plug in X. That just means you don't know. So in order to solve this, I need to isolate X by itself, so I'm going to add that over to the other side. Plus X, oops, plus X. Okay, so that means I have 2+ plus X is equal to 12. So that means X, if I subtract 2 on both sides, is equal to 10. So it means the number of electrons, which I'm going to write right here, is 10. Electrons. So I have 12 protons, 10 electrons. I have 2 extra positive charge, which gives that 2+ charge on the magnesium. Okay, so we solved all of the problems for the first bullet point. So let's move on to the second. So the second problem says, give an acceptable atomic notation for the following isotopes. There are 2 isotopes. One is strontium with a mass number of 88, and one is bromine with 44 neutrons. So let's start off with just giving the atomic symbol for strontium. That's right here, that's Sr. And for bromine, that's right here, that is Br. All All right, so there's two different ways to give the notation, but I'm just going to stick with the notation I wrote for magnesium. So for strontium, if I increase this, notice 38 is the atomic number. So I write a 38 down here in the lower left-hand corner. For bromine, it's 35, so I write a 35. And it says that strontium has a mass number of 88. Remember at the top left-hand corner, that's the mass number. And bromine has 44 neutrons, so that's not the mass number. The mass number, which is A, is equal to the number of protons, 35, plus the number of neutrons, which is 44. So that gives you 79. Okay, so I'd have a 79 up here. So that's an acceptable notation for both. Or you could have put something like this, strontium 88 or bromine 79. Both are acceptable. For this course, you're also responsible for knowing different types of chemical formulas. So two ways to express a chemical formula is through the molecular formula. So the example that I gave here is just to write each atom that is in that formula along with a subscript that indicates the number of each of those atoms that's in that formula. So notice ones are not shown. So for the case of CH4, just to give you a bigger blow up of this, there's no one seen right here, but this does mean that there's one carbon, and this 4 means there's 4 hydrogens. Another way is a structural formula. So see, these are the same two compounds that are shown above in the molecular formulas. CH4, but it's shown, the difference is I show how the atoms are bonded together. So the carbon has 4 bonds, each connected to a hydrogen. The line represents a chemical bond. And the 2 lines here show that the oxygen is the one that is connected to each hydrogen. So again, 2 sides of the same coin, just give you a little bit different perspective on the chemicals. All right, for this slide, I'm just going to reiterate and give a little bit and expand a little bit more on what the periodic table is. So periodic table of the elements is seen in front of you, and there's different pieces of information that are given. The first piece of information that is notable is this number in the upper left-hand corner. On different periodic tables, you might see it at the very bottom, but every time that you see a whole number like this, that stands for Z, its atomic number. So this gives the number of protons. So Z is equal, again, to the number of protons. So notice as we go across the periodic table, it increases. So we have 1, and then we have 2, then we go down 3, 4, so it increases going across and going down. Second piece of information that's notable is obviously the atomic symbol, which gives you the identity of the element. So we start off with hydrogen, then go to helium, down to lithium, beryllium, etc. I will give you a list of the names that you'll need to be familiar with, along with what information for the periodic table you'll have to know for upcoming quizzes and exams. Another piece of information is this number at the very bottom. So it's a decimal number. I'll blow it up a little bit more. So notice hydrogen is 1.008. Now I'm just going to give you a brief description of what this number comes from. This is the atomic mass of that element, or it's the amount of mass per mole of that element. Mole is just a really big number. We'll go into that a little bit later. But you can think of it right now as just the atomic mass for that element. So I'm going to erase this just so we have some more space to work with. Okay, each one of these at the very bottom is calculated from taking all the masses of each isotope of that element. So remember, an isotope is an element or an atom with the same number of protons but different neutrons. So for instance, hydrogen sometimes has 0 neutrons, sometimes has 1, sometimes has 2. And when the number of neutrons change, the mass changes, but the identity of the element does not, because the number of protons stays the same. So what this is, you can think of it as just an average of all the masses of that element that is found in nature. Okay, another piece of information is, notice at the very top, the columns are numbered, so that gives you the group number. And also the rows are numbered. These are the period numbers. And the way that the periodic table is arranged is to show that elements that are in the same group actually have very similar reactivities, and there's a reason for that that we won't go into right now, but that's the way it's formed. The last piece of information is, if we look down at the very bottom, that these groups are named to reflect the type of reactivity that they display. So first group is the alkali metals, excluding the hydrogen. The hydrogen really doesn't belong in that group. The second, color-coded, is alkaline earth metals. The third, so everything that you see in the light yellow, is transition metals. To the right of that are just basic metals, okay, in these green boxes. Then we can move a little bit over to the right. We have metalloids. So looking at silicon, germanium, arsenic, antimony, tellurium, polonium. Some are different depending on the periodic table that you look at, but in general, it's a little staircase going to the right here. Those are metalloids. Halogens are right here on the right-hand side, second to the last column, and the very last column are called noble gases. And then these last two, which are not, they are not main group elements. These last two are radioactive elements, are the lanthanides and the actinides. So you will need to know the names of some of these groups for upcoming quizzes and exams. This gives a little bit better picture of the distinction between the different sides of the periodic table. So in a broader group perspective. So notice everything that's yellow is a metal. So really everything on the left-hand side and at the very bottom is a metal. Those in pink are metalloids. And then everything that's green is a non-metal. So non-metals are generally on the right-hand side except for hydrogen. Metals are on the left and the metalloids are in the middle. And this gives a nice layout of what each feature on the periodic table corresponds to. All right, what is the group number, common group name, period number, and atomic number and symbol for the following? Okay, that's a lot. Okay, let's start with fluorine. I'm going to scroll down here. Okay, fluorine we can find right here. So the first bit of information that we need is the group number. So notice at the very top it says 17. So that's my first answer, is it's group 17. Common group name, the second to last group, they're called halogens. This is one of the groups that you will need to know. Period number, so the period number can be found right there. That is period number 2. Atomic number, that's the whole number seen there, and that is number 9. And the symbol, okay, the symbol is just what's in the box, and that's F. All right, let's do, I'm just going to put actually the answers for the last couple, and you'll see that in just a second. Okay, for the rest, you see xenon, okay, I cannot say that, xenon, iron, and beryllium. Take a look at that, see if there's any issue with it. Let me know if you have questions, and I'll see you for the next lecture. Or I really won't see you, but you'll hear me.